Manish Kumar, can you hear me?
Yes, ma'am.
Thank you. So we were on Lewis dot structures. Now we are going to move to formal charge. No chalk is good. Formal charge. Formal charge is equal to Fc. Formal charge is equal to total number of valence electrons. Total number of valence electrons minus total number of non-bonding electrons. Non-bonding electrons minus half into total number of bonding electrons. Total number of bonding electrons. So formal charge is equal to total number of valence electrons minus total number of non-bonding electrons, then minus half into total number of bonding electrons. Now let's consider, let's calculate that formal charge for ozone, O. You learn in this way only, that is O, this is the Lewis dot structure of ozone. Now I am writing it as 1, 2, 3. You have to calculate the formal charge on each and every atom in this ozone molecule, O3. Ozone, that is O3. So first one, this first one, total number of valence electron, that is 6 only. That is first carbon, number 1 carbon. Okay, first carbon. First carbon. Total number of on first carbon, formal charge is equal to total number of valence electrons 6 minus total number of non-bonding electron, that is 1, 2, 3, 4 minus 4 minus half into total number of bonding electrons 2, 4, that is 4. So it is charge is 0. Charge is 0. So I am not writing anything on that oxygen. Now I am going to calculate on second carbon. On second carbon, formal charge. Formal charge is equal to total number of valence electron, that is 6 minus total number of non-bonding electrons. See, 2 non-bonding bond, that is not in the bond. It is not participating in the bond. So 2 minus half into total number of bonding electrons 2, 4, 6. That is 6. So 3. So 6 minus 5, that is 1. So plus 1. So I am writing plus 1 here on second carbon, second oxygen, right? Second oxygen, first oxygen, second oxygen, third oxygen. Now on the third oxygen, what is the formal charge? Again we are using the same formula, that is total number of valence electrons 6 minus total number of non-bonding electrons. See, 2, 4, 6. 6 minus half into total number of bonding electrons. Bonding electron, that is 2. Here 2. So into 2. So 6 minus 6, 0 minus 1. So this is minus 1. I am writing a minus charge on this oxygen. Minus charge on this oxygen. So this way you can calculate the formal charge of different atoms in a molecule. Formula is what? Total number of valence electrons minus total number of non-bonding electrons minus half into total number of bonding electrons. So every element is trying to get 8 electrons in the outermost shell. In the case of helium, it is duplet. In other cases, it is octet. So octet means if they get 8 electrons in the outermost shell, they get stability. That is the reason why they combine with each other. They enter into chemical reactions to gain 8 electrons in the outermost shell. So when we were doing the Lewis dot structure of different compounds, we made it clear that every atom should get 8 electrons. In that way, we pulled electron pairs. So that is octet theory. We are pulling electron pairs to make the bond to make 8 electrons on each and every atom in a molecule. So is that the only criteria? There are limitations to octet rule. What are these limitations? What are these limitations? We said every atom is entering into a chemical reaction, or their atoms are combining with other atoms to get 8 electrons in their outermost shell, octet. Now let's see what are the limitations of this octet rule. Write the heading, limitations of this octet rule. Number one, LiCl, BeCl2, BH3. In these compounds, the central atom is not having, say, lithium. Lithium is not having 8 electrons. Be is not having 8 electrons. B is not having 8 electrons. So in these cases, central atom is not having 8 electrons. So that is one limitation to the octet rule. Second limitation is that odd electron species, in odd electron species, for example, NO2, NO2. This is an odd electron species. How odd electron species? 5 plus 6 plus 6, that is 12, that is 17 electrons. Nitrogen, that side oxygen, oxygen, minimum 1 bond, 2, 4, 6, 8, 10, 12, 14, 16. Now see, only 1 electron. In odd electron species, see, the nitrogen cannot have 8 electrons. 8 means it's an even number. So in odd electron species, this is an odd electron species, the central atom is not having 8 electrons. The central atom is not having 8 electrons. So another deviations for the octets. And the next is what? Expanded octet. Means more than 8 electrons around this atom, more than 8 electrons. For more than 8 electrons, you can consider this phosphorus. Phosphorus pentachloride. Phosphorus pentachloride. Central atom is phosphorus. On this phosphorus, around phosphorus, you can see 5 bonds. 5 bonds means 10 electrons, more than 8. It is called an expanded octet. Expanded octet. Similar is the case with SF6 and H+SO4. Here, SF6 central atom is sulfur, fluorine, 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 fluorine. In this central atom, sulfur is having more than 8 electrons. So this is another example for expanded octet. Similarly, in H2SO4, sulfur is having more than 8 electrons. Here see 1, 2, 3, 4, 5, 6, 6 into 2, 12 electrons are there. So we cannot say that to get 8 electrons, atoms are participating, or atoms are combining with other atoms. Atoms are entering into chemical reaction. We cannot say this. These are the limitations of octet rule. And H2SO4S in H2SO4, see 1, 2, 3, 4, 5, 6, 6 into 2, 12. 12 electrons are there around sulfur. Again, a limitation or drawback of octet rule. Xenon is having 8 electrons in the outermost shell, so it should not have taken part in any chemical reaction. But xenon is making so many compounds. That means that is not the ultimate aim to get 8 electrons by combining. To get 8 electrons is not the ultimate. So we are giving some examples to show that to show the limitations of octet rule. In all these cases, xenon is a noble gas. It is having 8 electrons in the outermost shell. It should not have taken part in any chemical reaction, but it is taking part in many chemical reactions and make many compounds like XCF2, XCF4, XCO2F2, XCOF4. Similarly, many compounds are formed of xenon. So this is a limitation of octet rule. Next, we are moving to the lattice enthalpy. Now, for a process to take place, ultimately some energy is to be released. When you compare the reactant's energy and product's energy should be less than the reactant's energy for the process to be spontaneous. For a process to be possible, feasible, reactant's energy and product's energy, total amount of energy of reactants, total amount of energy of products, if you check, if the product's energy is less as compared to the reactant's energy, then the process will be spontaneous. Means released, some amount of energy should be released. Some amount of energy should be released. You should compare the reactant's energy and product's energy. You consider the formation of NaCl. Na is from Na plus is to be formed. For the formation of Na plus from Na, you know that 946 kilojoules of energy is required. That is plus, sorry, 496 kilojoules of energy is required. That is 946 is the triple bond enthalpy of N triple bond and N triple bond. 946. Numbers are same. This is 496 kilojoules of energy is required to convert this Na plus from Na. So one electron is removed. Now Cl atom takes one electron and Cl minus will be formed. So here delta H, that is delta Ege, is equal to minus 349 kilojoules per mole. So this is the amount of energy released, that is the amount of energy required. So ultimately when we compare this plus and minus, 496 then minus 349. That is plus 147. Plus 147 means this much amount of energy is required. Energy required, the process will not be spontaneous. Energy released, process is spontaneous. अपने आप चलते. So this reaction NaCl cannot be formed from NaNCl. Look at this value plus. If it should have been a minus value, we can say NaCl can be easily formed. But this is plus required. Who will give this? Released. If it is released from itself, it can give. But required from some other source, they have to take it. So this process should not have been spontaneous. NaCl should not have been formed. But we know that NaCl is a famous compound, stable compound. So much of NaCl you see, seawater contains lots and lots of NaCl. So NaCl is a feasible process. But how can it be feasible? See, plus 147 plus value, energy is to be absorbed. Energy is to be absorbed means it cannot be a spontaneous process. Energy is to be obtained from other source. So, what is the reason for the spontaneity of this process? Anyway, lots and lots of NaCl you can see in this world. That means it is a stable compound. How it is formed then? If we say 147 plus, then how it is formed? If it is minus, then we said, okay, NaCl can be easily formed. But here, looking at this value, we say NaCl cannot be formed. But we see NaCl, lots and lots of NaCl around the world. Seawater, so much of seawater, and it is very salty also. So, NaCl is formed very well. What is the reason for that? There we come to know this lattice enthalpy. See, when this Na plus and Cl minus, so many Na plus and Cl minus come to take the position in the crystal lattice to form the crystal, lots of energy is released. How much energy is released? Minus 788 kilojoules of energy is released. So see, that much a heavy amount of energy is released. That will be more than compensated. So this will be more than compensated by that minus. That can compensate, that can more than compensate this value, or this value can be more than compensated by that high negative value. So that is what is meant by lattice enthalpy. So when Na plus and Cl minus they come to form the crystal lattice. They come to form the crystal lattice. So many Na plus and Cl minus in the gaseous state. I will be writing Na plus in the gaseous state. That ionization enthalpy in the gaseous state, electron gain enthalpy in the gaseous state. So we have got Na plus and Cl minus. So many Na plus and Cl minus in the gaseous state. And then when they come to sit, or when they come to occupy the lattice points to make the crystal, each point, this point, this point, this point, this point, this point. This is Cl minus, Na plus, Cl minus, then Na plus, Cl minus, Cl minus, Na plus, like that. Each and every corner where there is a crossing, you can say where there is a crossing, there you will find an atom. So when these ions come to occupy the lattice points, lots and lots of energy is released. That energy is called lattice enthalpy, that is minus 788. So this minus more than compensates that plus 147. Then what is the definition of lattice enthalpy? Definition we always say in the form of required, 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 required. So when those ions come and sit this position, this much amount of energy is released. Means when those ions come to take the lattice position, this much amount of energy is released. Means if you give this much amount of energy, this will be broken to form those ions. If you give 788 kilojoules of energy to this, it will be broken to form those so many Na plus and so many Cl minus. So we are going to write the definition in this format. Lattice enthalpy is the amount of energy required to break 1 mole of solid ionic compound into gaseous constituent ions. Write down lattice enthalpy. It is the amount of energy required to separate. It is the amount of energy